Well, gravitational potential at a point inside a solid sphere. So we are considering a solid sphere like this whose density is constant inside and mass is m in total. Okay, so total mass is m. Density is rho, which is constant. Well, so the external radius of this sphere is r. And now we are considering a point inside, say somewhere here, which is at a distance r, small letter r, from the center of the sphere. And the point is named P. So this is point of interest. And we are finding, okay, so we are finding the gravitational potential at P, point P. So this is Vp, this is what I am calling. And now I have to take this situation like this, so I have to split this sphere inside in this manner. Okay, so the inner portion is of radius r and the exterior of radius capital letter R. So inner is a smaller sphere, right? So this is a small sphere inside, of a radius r and density rho. Now at point P, the gravitational potential is nothing but the gravitational potential due to the small sphere inside plus, so now you have to think about the remaining portion which is in between, so this surface and this surface. It can be treated as a shell. Okay, so this is the shell what we can treat. So this is a shell. With external radius r and internal radius small r. Okay, so the whole mass is now split into two things. One is the solid sphere. Okay, so one is a solid sphere like this, which is inside, whose radius is r, and another one is a shell like this, which is treated like this, So this is where the mass is distributed in the shell. So we are seeing a kind of cavity inside. Okay, so now the point of interest P is lying somewhere here. Okay, so P is lying somewhere here. This is what we are treating. So that means the potential at P is equals potential due to small sphere inside and the potential due to the shell, right? So potential due to the shell. So now the potential due to smaller shell is given by, so this is V small is equals minus G into mass of this shell, the solid sphere inside, so which is given by 4 by 3 pi, right? So it is rho, it is density into r cube. So this is how we can write, and divide by r. This is the way how I can write the potential due to the smaller sphere inside what we treated here. So this is further can be treated, otherwise written like this, 4 by 3 pi g rho r square. So this is V small, say it is 1. And now we have to do for this shell. So potential due to shell to be found. So for this, what we have to treat is, now in this drawing, I am simply considering a small elemental volume here. So this red mark what you are seeing, okay. So this is of width to dx, and from center it is at a distance x. So now gravitational potential at P due to the element is dV, which is equals, this is because of shell what we are finding. So this is equals, how we can write is minus g into dm divided by x. So here dm stands for the mass of this small element and mass dx, okay. So this one. So this can be assumed or written like this, but dm is equals, how we can write dm? It is nothing but the area, surface area multiplied by the width of this element, which is dx. So otherwise I can write 4 pi x square into dx. So now this d shell, dv shell can be written as minus g into 4 pi x square dx divided by x. Otherwise dv shell is equals minus 4, otherwise I write g multiplied by 4 pi x into dx. So now in order to find the total potential at P due to the shell is simply the integration of this result, means V shell is equals minus 4 pi g integration x dx. The limit should be taken from the interior radius to exterior. So that means x varies from r to capital letter R. Okay, so now what I can write is V shell is equals minus 4 pi g into, so I am missing one thing, that is the density term. So density term should be added along with this. Okay, so this completes the meaning of dV shell. So that should be written here along with the minus 4 pi g rho. So the integration, result of integration is x square divided by 2. The limits are this much. Okay, so on putting the limits in this equation, we get minus 4 divided by 2 pi g rho, and inside bracket r square minus r square. So I got this. And now the Vp is, therefore Vp is nothing but, right? So we have to find the gravitational potential at this point. This is nothing but the sum of V small plus V shell. So for this I am writing Vp is equals, so V V small is of minus 4 by 3 pi g rho r square, and this one which is minus 4 divided by 2 pi g rho into r square minus r square. So on doing further calculations, this is what I can take outside is minus 4 pi g and rho. I can keep all these things outside. Also I can keep 3 in the denominator outside. So inside the things remaining are r square plus it is 3 divided by 2 into, in the bracket I can write r square minus r square. So Vp is equals minus 4 divided by 3 pi g into, so what actually this rho is? So this rho is the density of this big sphere. Okay, so now density can be written as density is equals to mass divided by volume. So mass of the bigger sphere is equals density is equals mass divided by volume is 4 by 3 pi r cube. This is what I can write for density. So I am using that notation say here. So m divided by 4 by 3 pi r cube, and inside bracket I can write it as it is 2r square plus 3r square minus r square all divided by 2 inside bracket. So 4 by 3 pi, 4 by 3 pi get cancelled. So Vp is equals to minus, right? So it is g into m divided by 2 into r cube is 2r cube, and inside bracket what I can write is 3r square minus r square. This will be the important result for further calculations regarding the gravitational potential at a point inside solid sphere.